Okay. So, let's see. We were talking about maximally symmetric spaces and conformal algebra. I'm just wondering, maybe I should review some of it or just continue?
I got through most of your lecture. I missed like the last 15 minutes, but I think I would be okay for there to be some notes.
You just started from the conformal.
Yeah, all right. Let me start from the conformal business. The basic idea is that, well, if you have an isometry, it's G prime IK of X is actually GIK of X. In equation 136, or rather 9.136, I have primes on the X's, but of course you can take them all. This is an isometry. And as I said, there are these are very strong conditions, and in the standard model, the present standard model of cosmology, which is lambda whole dark matter, or vacuum, dark energy, cold dark matter, the space is a maximally symmetric three-space, and then time is a separate variable, and the scale factor depends upon time. And so those three kinds of maximally symmetric three-dimensional spaces are characterized by isometries. And they're a three-sphere in 4 dimensions, just Euclidean three-space, and a three-dimensional hyperboloid. I actually added to the class notes, I added the metrics of those to the class notes. Now, this is a very restrictive condition, and in fact, in three-space, there are only 3 maximally symmetric spaces. And it's amusing that we use all of them in the standard model of cosmology. A much more flexible condition is that metrics are conformally related. Now I'm going to add a prime on the X, because this will facilitate computation. So I'm going to review the last part of the lecture. So this is G prime of X prime is just in general XL comma I prime XM comma K prime GLM of X, and whereas in an isometry this would actually be GIK of X prime, here we allow it to be omega squared of X prime GIK of X prime. So this is where we say the relation is it's a conformal relation between metrics. So that's the other condition. By the way, are you guys all familiar with this notation?
The common notation?
Yeah. Okay. And comma prime, let me just make it abundantly clear. Comma I prime is partial XL, partial X prime I. So the prime here doesn't so much refer to the I as to the variable. Okay. All right, now, as we did last time, we considered infinitesimal transformations. X prime L is XL plus epsilon YL. And we took omega squared to be 1 plus epsilon, I just call it omega of x prime. And so then if we just substitute these expressions into this equation, what we get as the conformal condition is GLM delta Li minus epsilon Y L comma I delta MK minus epsilon Y M comma K is equal to 1 plus omega epsilon omega times GIK plus epsilon YL GIK comma L. Well, that becomes a lot simpler when one makes use of the Kronecker deltas. We have the GIM YM comma K plus GLK YL comma I plus YL GIK comma L plus omega GIK to 0. So that's basically Killing's conformal condition. So that's Killing's conformal condition, and now what you can do is you can multiply by GIK, and what you get then is delta Km Ym comma K plus delta IL YL comma I plus GIK YL GIK comma L plus, and over here you get 4 omega in 4 dimensions, but you get d omega, and let me write this as omega d, so we don't think of d as a differential. It's one of the unfortunate in d dimensions. D space-time dimensions. And of course that is a much simpler equation. It's 2 yk comma k plus yl gik comma l plus omega d equals 0. So that's what we get. But now we can go one step further, because this obviously is an equation for omega, and this tells us that this conformal factor omega is minus 1/4, well, minus 1 over d. 2 yi comma I plus yl gik gik d lower ik comma l. And if we put that equation into Killing's conformal condition, which is this equation, then we maybe instead of just doing that directly, I will go to the next line. We get GIM YM comma K plus GLK YL comma L plus, well, I'm sorry, I just screwed up a little bit here, because This is the equation for if omega equals 0, then we get this equation. So this equation is plus YL GIK comma L equals 0. So this is the condition when omega is actually 0, but more generally, of course, it's whatever you get by substituting that in there, and I might as well write it down since it might, well, we're going to use it one way or another. LK YL comma I plus YL GIK comma L minus, and now this is the omega thing, and right, okay, minus 2 over D Yj comma J plus 1 over D YL GJN comma L GIK equals 0. So this is the full-blown conformal condition. But
so, Kevin, what's the superscript that you've written here on this? You have if
this
omega.
one here?
No. The superscript on the term to the left on the y.
I think it's supposed
The
to be
superscript
L
on-
comma I.
Is that
okay, that's good because you're right. There's something a little screwed up here.
I think the subscript's supposed to be an I.
Right. This is comma I. Thank you.
comma I, yeah.
Okay, so you guys get some candy. So, Austin,
Just your candy store.
Bobby,
Here, you have your candy store as well.
Sure, thanks.
okay, so that's what we've got now. Kelly's conformal condition over here, we can write it more simply if we use the fact that covariant derivatives vanish. So GIK semicolon L is identically 0, and that allows us to simplify this equation. And I showed that to you guys, I think Monday last, when we were in the general case as opposed to the conformal case. Well, maybe actually it's the isometry case that's specific. Conformal case is
Yeah,
more general.
the conformal case is more general. I thought
Yeah,
the
yeah,
symmetry
yeah.
condition was the-
Anyway, applying this, what we get is yi semicolon k plus yk semicolon I plus omega GIK equals 0. So that's that's a much more condensed expression, and we can also write this as the y lead derivative on GIK is minus omega GIK. So that's another way of writing it. Now, so far today we've been in a general space-time, and what we're going to do now is drop down to flat space-time and consider these conditions in flat space-time. And the first thing is to go back to this equation for omega, which is this. Well, in flat space-time, the metric doesn't depend upon position, so this term vanishes, and so we just have minus 2 over d. So GIK now goes to eta IK, but we can stay in D dimensions, and now we have that the conformal factor is minus 2 over D yi comma I. So that's what omega is. And then in flat space, covariant derivatives become ordinary derivatives, and so this equation, this Killing's condition, becomes simply yi comma k plus yk comma I is 2 over D eta ik yl comma l. So that's this is Killing's flat space condition. So K's I'm having trouble with this K. K's flat space conformal condition. Okay. Now we're going to analyze this for infinitesimal transformations. X prime I is xi plus epsilon yi. And yi is going to be called one of Killing's conformal vectors, or flat space conformal vectors. So I don't know where to put all these adjectives, but we'll just leave it like that. Well, we already know some of these. It turns out all the Poincare transformations, in other words, the translations and the Lorentz transformations, are conformal transformations of flat space-time. And we can see that because, in fact, not only are they conformal transformations, but they're actually isometries because they leave the metric invariant, don't they? Right? So a translation, x prime I is xi plus ai. This leaves the metric invariant, leaves the flat space metric invariant, but also x prime I equals, let us say, bij xj, where bij is minus bji. This is a small, well, I'm screwing up again here. When my left arm is down, you've got to be careful. X prime I equals xi plus epsilon bij xj, where B is antisymmetric when both indices are down or up. This is a Lorentz transformation. And of course, Lorentz transformations, as we know, leave the metric invariant. So they're actually isometries of this. And in particular, for these cases, you see, for the translation, yi is just ai. So maybe, in fact, I should write plus epsilon ai. So for translations, yi is ai, and consequently, yl comma l is 0, and the left-hand side is also 0. So the translation satisfies Killing's flat space conformal condition. For the case of Lorentz transformations, we have bij, then yi is yi is, let's see, what is yi? Is yi bi? I've got two indices here. yi is bij xj. So now, if you do yl comma l, you get 0 because this thing is anti-symmetric. So it has zeros on the diagonal. It doesn't matter that there's one index lifted because that only changes a sign. It doesn't turn a 0 into something non-zero. And then the rest of it over here is BIK plus BKI. That vanishes because B is antisymmetric. Okay, so that's that. The next step is what's called a dilation. And it's kind of evident that that if you let x prime I equal to sigma xi, then effectively dx prime I is sigma dxi. And so what you can have is omega squared of x prime I, eta ij, or did I have ik? Ik dx prime I dx prime k is equal to, we want that to be eta ik dxi dxk, and so since these guys pull in, this is actually omega squared of x prime eta ik sigma squared dxi dxk, and so all we need here is to have omega squared be 1 over sigma squared, and then that cancels that. So dilations are conformal transformations. And some people, I would say, call a dilation a dilatation, but I think that that's just bad English. So, I mean, it's not wrong, it's just needlessly pretentious and stupid. But you find it in the literature of particle theory. Somebody needs to apologize. The other kind is what's called an inversion. And let me say what that is. That's x prime I is equal to, let us say, r squared xi over x squared, or equivalently r squared xi over, let us say, xk xk. Okay. So this is called an inversion, and it is a conformal transformation. To understand that, more fully, let's see that it actually satisfies Killing's flat space condition. Well, we have dx prime I is r squared over x squared delta ij minus 2xi xj over x squared dxj. So I worked that out with my fingers, but in the notes I just wrote the final condition down. So if xi prime is equal to that, then dxi prime is this. And if I just write omega squared for omega squared of x prime, just to save some chalk, then the conformal condition is omega squared eta ik d prime r x I d prime dx prime k. It will be equal to omega squared eta ik. Then we're going to have r squared over x squared squared, and then we have two parentheses. One is delta ij minus 2xi xj over x squared dxj delta kl minus 2x kxl over x squared dxl. And so this is omega squared. Now I'm going to use the eta ik and the deltas in there. And so this is r squared over x squared squared. And now what we've got is eta jl from this hitting the two deltas. And then we have minus 2 eta jk xk xl. So this one was this eta hitting this delta, so that turns the eta into eta jk, and that's the delta. And the other one hits this, and we have xk xl over x squared, and then the cross term is 2 eta il xi xj over x squared, and then the last term is 4 x squared xj xl over x squared squared, and that's all times dxj dxk. Well, this stuff collapses. In fact, it collapses completely because all the terms cancel except for the first one. And so this is just omega squared, r squared over x squared squared, eta jl. JL, I think this was J. This was an L. Eta JL dx dxl. So what this says is you just need to define omega squared to be x squared over r squared squared, and that works. So an inversion is a conformal transformation. A translation is a conformal transformation. But now an inversion is not an infinitesimal transformation. On the other hand, we can get an equivalent, let's see, an equivalent, we can get an alternative infinitesimal conformal transformation by combining translations, by combining translations with inversions. And so what we're going to do is first let xi go to xi over x squared. This is an inversion. Let this go to xi over x squared plus ai. That's a translation. And now let this go to another inversion. And this would be then xi over x squared plus ai, all divided by eta jk xj over x squared plus aj xk k over x squared plus ak.
So an inversion is essentially, if we want to perform an inversion transformation, that's like we take all the points outside of one area of the region and map them into that area, and then map all the points inside that area. For instance, if we just had like a lambda like this, something like this, right, and we'll call that sigma. We take all the points outside of this, and then map them into this, and then all the points in this and map them out of this. That's an inversion. Is that what an inversion is? Is that what we're trying to do?
I don't know. I haven't, I mean, it must be something like that because that's the way the term is, that's what the English word means. But I don't
literally invert the space.
I mean, all right, look, if you're in Euclidean space, it probably means something like that. Because if you're inside the unit sphere, then x squared is less than 1, and so you go outside the unit sphere. And if you're outside the unit sphere, x squared is greater than 1, and so you come in. So it maps the inside of the unit sphere outside, and the outside of the unit sphere inside. That's in Euclidean space. But in Minkowski space, I'm not sure quite what it does.
Yeah, I guess it's hard to visualize.
And remember, we're in a general flat space-time, so we could be in a space-time with S space dimensions and T time dimensions. In fact, I really encourage young people to think about several time dimensions. This has been something that hasn't been taken up very much in physics. I'm not sure why, but...
Because we can't think about it.
What?
Because nobody can understand it or think about it. Well, I don't know. What would it mean to... I've read where people talk about it, and there's like a paragraph and that's it.
Like a what?
One paragraph, or even 2 sentences, and then they just go...
We talked about this at one point. We think of like almost like a confinement, and we only see, for some reason, we're only able to observe one time dimension, right? But maybe there's 3.
Well, I mean, that's... Yeah, you can say that you're only somehow able to observe one time dimension, or you're stuck on a time... what's the term? Brain. I don't know. I have devoted less than 6 hours to think about this. Okay? So I have not really followed my own advice, but I think it's amusing. And one of the things that actually comes in automatically is if you imagine classical physics with 2 time dimensions, you'd automatically have something like a wave function, because the particle at any time, a classical particle at any point in one time variable, wouldn't be at a particular space point because there are many other time variables, and so it could be at many other space points. But of course, now that I think about it, if there's only one other time variable and it's compact, then if you moved in that other time, say in a circle, the classical point would do a closed orbit in space. On the other hand, if the other time variable is infinite in extent, then the thing in space could, well, it would be an infinitely long line. That still isn't the same thing as quantum mechanical wave function. So I don't know. But of course, there's no reason to say you have to do this classically. You can do 2 time dimensions quantum mechanically. Anyway, it's interesting, and it's worth.
One question before we go on.
Yeah.
So this last one here is another inversion, right?
This is just x prime. This is x prime squared. In other words, we're going. This is the inversion. This is the translated inversion. And now if you call this, and you think if this is xi, then this is xi squared in the denominator. And so this is an inversion of the translated inversion. Let me get you a...
Well, the A, on that first one, the AJ, the J should be a superscript, correct?
Yes.
Oh, because there's a square.
So let's see. I've got to give you guys some more candy. Here, you must get at least one.
So it's like, yeah, I guess the reason why you're saying an inversion is not necessarily infinitesimal is because there's a rather drastic change to some points.
Right, and you can see that in the case
But if
of
you sort of invert, translate, invert, yeah.
Euclidean in space, in the d-dimensional Euclidean space, it's pretty clear. And the Minkowski case, I don't know, I'm confused by it. In any event, let's go to the infinitesimal case. So the infinitesimal case is A is tiny. So if A is tiny, then x prime I is this expression here. And if we just multiply out the denominator, what we have is xi over x squared plus ai divided by eta jk 1 over x squared from the product of these two terms with, why is there still an eta jk there? I think that's a mistake, actually. Yeah, that's a mistake.
No, I think it's
So hold on, there's a typo here.
But if I would imagine the A to JK is cool because if A is equal to 0, then this is just the identity map, right?
Yeah, it would have to be.
Yeah. So I feel like the A to JK is necessary because if you set A equal to 0, then you'd have x squared over x to the 4, right? Then that so if you set A to 0. Wouldn't the xj, xk, a to jk?
Actually, I have worked it out.
Sorry,
So
okay, sorry.
We don't need to guess.
Yeah.
Xj, a to jk, xk is x squared. So it's x squared over x to the 4th. That gives you 1 over x squared. The next term is, for example, a to jk, xj gives you an x lower k, and if you combine that with an ak, you get x dot a. You go the other way, you get also x dot a. So this is 2a dot x over x squared. And then finally, you have aj, a to jk, ak, that's just a squared. And now you multiply top and bottom by x squared, and what you get is x squared x I over x squared plus ai, and you're dividing by 1 plus 2a dot x plus a squared x squared. So that's what we've got. But now we take advantage of the fact that a is tiny. And so this is in fact xi plus x squared ai, the top thing. And then it's divided by this. But a is tiny, so we drop this term. And 1 over 1 plus tiny is 1 minus tiny. And so this is 1 minus 2a dot x. And altogether we can rewrite this as xi plus ak a to ik x squared minus 2 xi xk. Okay. So this is the other conformal transformation. So we have basically the conformal algebra. I'm getting a little bit ahead of the story here. Is the Poincaré algebra plus dilation, a dilation plus this conformal transformation. Okay, so that's the conformal algebra. Those operations. Now let's go back to Killing's condition, and I've got so many equations on the board that, well, let me actually write it down, since here I do use equation numbers in my notes. I'll put this on the webpage this afternoon. So what we've got is yi comma k plus yk comma I is 2 over d theta ik yl comma l. Okay, now if we, that's called Killing's conformal condition, flat space conformal condition. And now suppose we differentiate it. Well, if we differentiate it with respect to, we operate on it with respect to di, then what do we get? We get d dot y comma k plus plus d squared yk is equal to 2 over d. In fact, this common notation is a hell of a lot easier to use than this other notation. So it's that. So that's what we get. Or if I rewrite this, this is y L comma L comma k plus di yk is 2 over d y L comma L. All right, I've got my i's and, oh, I forgot the eta ik. This eta ik takes the I and brings it down to a k. Sorry. Okay, well, these two terms are the same apart from the factor, and so what we get is 1 minus 2 over d times, I'm using all sorts of notation. Okay, so that's what we get, and we notice if d is equal to 2, this is a much simpler equation. If d is not equal to 2, then it's a more general equation. And in fact, we can go one more step. We can differentiate one more time. We can take the derivative with respect to k. And if we do that, what we have is 1 minus 2 over d di dk yk is equal to the same thing over here, minus di yk, comma k, just to write things in, well, yeah, I mean, it's all right, I screwed up again the notation. So what do I have over here? Oh, I made it worse. All right, hold on. Okay, it looks like that. And then if we combine things, I think I'll just use what the notation of my notes. So that's what we get as the equation. And so we see that if d is equal to 2, then the equation, wait a second, what did I do here? Hold on. I think I've gone off the rails here. So certainly this equation, if d is 2, then this equation just says that yl comma l comma k is 0, and all right, well, let me give you the conclusion. I seem to have gotten something confused. I'm confused about something here. If d equals to 2, if d is 2, then this term is 0, and
I think we can see that from the third equation. I think you can see this relation from the third equation there. The third one.
or maybe I should, let's go down from, this equation's okay, right?
Yeah.
And is this one all right? Okay. So that is certainly that. This is that, and that's all right. 2 over d, so this equation is right.
Yes.
So you're saying there's
This is one. I think.
a problem here.
The coefficient should change. It should switch.
Oh, that's right. There's a screw up over here. I should have just followed the notes. Instead, I tried to change the notation. Yeah, right, great, thank you. Okay, this is what I meant to say. And so if d is equal to 2, this term vanishes, and this equation is just box yk equals 0, and so this is just Laplace's equation in whatever the flat space is. And so in 2 every solution of Laplace's equation is a conformal killing vector. And moreover, there are infinitely many of those solutions. So you have infinitely many solutions. So there are infinitely many killing vectors.
I have a question.
Yeah.
Can we go back to the one that you just changed?
The left.
On the left-hand side, should that be YL, comma L, comma K? So 1 minus 2 over D multiplied by, shouldn't that be the YL, comma L, comma K instead of partial I, YK? Is that, am I right or am I missing something? So the,
Yeah, I combined these two
Yeah, but those two are not
and
equal.
moved this over there.
Yeah,
you have partial I,
Let's look
partial
at
I
them.
twice. On the left-hand side, after the
Where? Here?
down, down 1.
Right.
Now look what's multiplied by 1 minus 2 over D.
Yes, you're right. You're right. That should be.
That should be the YL, comma
Yeah.
L, comma K.
Yeah. Let's just. This is. Oh, actually, my notes seem to be wrong here. So this is del dot y, comma k. All right.
And del dot Y is Y upper L, comma lower L.
Yeah, this del dot y is
Right.
okay, and so this equation also is right. This equation is correct, and all right, let's forget about this a little. Oh, but you could differentiate again. And if you differentiate again with respect to yk, then what you've got here is minus di d dot y. And if you differentiate again with respect to k here, you get 1 minus 2 over d yeah, this is then di del dot y. That's what I was trying to say. And then you can move this over there, and you then get this equation. So that's how everything works. Sorry for the... I should have just followed my notes instead of trying to improvise on the fly. So I owe two of you some candy. And so in any case, if we go back to this equation, and we say we're in 2 dimensions, this term cancels, and we just have box y equals 0 in 2 dimensions. That's Laplace's equation, infinitely many solutions. If we're not in 2 dimensions, then we have a more complicated equation, either this one or that one. Or in fact, we have both equations. All right, let me give you guys the candy that we deserve here. Why don't I give you 2 of them? 2 dimensions. Then we have this equation here, and the most general solution is actually, for an infinitesimal case, is actually yi is ai plus bik xk plus dk eta ik x squared minus 2 xi xk. And let me just check this, because I'm a little confused here that this thing here is this exactly the same as what we got over here? Yeah, it is, isn't it? Eta ikx squared minus 2. So this is what we call the conformal transformation over there. This is a translation, that's a Lorentz transformation. Where's the dilation? So let me just... I left a term out. This is equation wrong in the notes. Okay. So, there's the dilation. So, translation, Lorentz transformation, dilation, and then what's called a conformal transformation, because it's a conformal algebra and there's no other nice term for that. So so those are that's the most general killing vector, and for the flat space conformal transformation. And now we can go to the differential forms of these. And the differential forms are pi this is a translation, and that corresponds to the momentum operator, so that's di. Then we have j ik. These are the Lorentz transformations. xi dk minus xk di. And then it turns out that the dilation operator is xi di, and the conformal generator is eta ik plus times eta ik, well, it's just x squared, minus 2 xi xk dk. And so now we can compute the commutators of these generators, and some of them we know already, namely pi. Well, let me use other indices. The 4 momenta, or the d momenta, these all commute with each other because derivatives commute. It turns out that the k's also commute. In fact, let me, just in case there's a typo here, let me use. So the k's also commute. Why did I write a subscript? So I wrote a subscript because I wrote the j's down. well, anyway. So the K's, KI, KK, or KL, these commute. But what we knew originally was, just from knowing how the knowing the Poincare algebra, which we studied last semester, this would be Jij, comma PL, and so this behaves as a Paul vector under Lorentz transformations, and so we get minus eta IL PJ plus eta JL PI. So these are two of them that we knew about. Let's leave that aside, why that one is 0. Then there's also the most complicated of them all is actually IJ JLM. So this is the commutator of two generators of Lorentz transformations, and this is minus eta IL JM minus eta JM JIL plus eta JL JIM plus eta IM JL. So these are the ones that we already knew about. And now what we can do is compute from these differential formulas what the D's are. And one right away is what is D? Well, D with itself has to be 0 because things commute themselves. Let's do D with P. So D is, let us say, xk, or let's put xk dk, and P, of course, is, well, it would be D upper I. And so how does this go? Well, all right, let's lower this one. And let me just lower this one just to make things simple. So this one, this on that is xk dk di minus di of xk dk. And so the extra term is minus delta ki dk, which is to say minus eta, well, all right, we can just say minus p lower k. So minus p lower I. So what we have is dpi is minus pi. And so D with J is actually 0. And let's see if we can work this out. D, J, So let's use it, Ij, and we'll have here xk dk, and let me lower the I and j, simply so we have derivatives down like that. So this will be xi dj minus xj di. So that commutator. And what we have here is, if we just try to keep track of the non-zero terms, the dk on the xi is xk, and we can call xi eta I. Well, if I do this slowly, I'm just trying to get the minus sign right. It's xk dk on dj eta il xl. So that's this term. And then, but it actually hits both terms. So let me do both terms. So the other term is minus eta jl xl di. So it's all of that. And now the k comes in and hits the xl, so this is xk eta il delta lk, and then a dj, and then over here it's minus xk eta jl delta lk di. But that's, I've just done the terms going that way. Going the other way, we've got these terms that can act on this, and that's a little bit simpler. That is, so it's minus xi delta kj dk plus xj delta ki dk. So we have to cancel out these terms on those terms, and let me see, they actually completely cancel, and it's not immediately obvious to me why that should be the case, especially since there's hardly any blackboard left. All right, let me just take these terms and use the delta, so use the deltas. So this is eta ik, and so that's going to be xi dj, okay, minus, over here we're going to have eta jk, and that means xj di. So that's those terms. And then over here we have minus xi dj. And then this one gives us xj di. Now all that should cancel, and indeed it does. So that gives us the rule that the dilations and the generators of Lorentz transformations, those commute. I think what I'll do is I'll assign as a homework problem the remaining commutation relations. we have had a shortage of homework problems, and this would probably,
We haven't gotten any back.
what?
We haven't gotten any back.
Well, the homeworks go to the grader.
She's saying that he didn't grade some.
Oh, yeah, he grades them, and if it's not obvious to him how to grade them, then he asks me for solutions, and I send him solutions. Okay, so I guess we can, is there any question, or should we just turn this off?